Hi everyone, welcome back to the course on quantum theory of many-body systems in condensed matter. My name is Luis Gregorio Dias. I'm a professor at the Institute of Physics at the University of São Paulo in Brazil. And today we're going to continue our series on phonons and electron-phonon interactions towards the BCS theory for superconductivity. And our topic today is RPA for the electron-phonon interaction. And then we're going to discuss Cooper instability. So we're going to start off by combining the electron-phonon interaction we saw in the previous class with the actual electron-electron interactions coming from Coulomb repulsion, and show that that leads to, or can lead to, an attractive interaction, effective attractive interaction between the electrons. Then we're going to do RPA. We did that for the electron-electron interaction already, but we're going to do that for this effective electron-electron interaction. And then we're going to see how that leads to the so-called Cooper instability, where these electrons which are attract to each other actually form pairs. And then we're going to estimate the critical temperature where this Cooper instability takes place. That, of course, will lead us to talk about BCS in the future. So essentially, that's the path we're going, right? So let's get to it. All right, so let's start by reviewing the effective electron-electron interaction we derived in the previous class. There should be a link to that class over here. And we started with the electron-phonon interaction added to the non-interacting part of the total Hamiltonian, and this non-interacting Hamiltonian H0 is essentially the sum of the free electron part, so these are fermionic, plus the free boson part, and so these are bosonic operators, plus the electron-phonon interaction, which we covered in the previous class. So we have two fermionic operators, a creation and a destruction one, and this operator, which is the sum of B dagger minus Q plus B of Q. All right. And then we proceeded to calculate the Matsubara-Green's functions for the electrons, for the electron spin sigma, momentum K, defined as this. And we realized that we could write this as a perturbative expansion in when we move into the interaction picture, where the interaction would be mapped from this electron-phonon term into an effective quartic term. So this is a term which is quartic in fermionic operators, so is an interaction, right? And this interaction is mediated by the phonons. So here the coupling involves this propagation of a free phonon from, say, time tj, tau j to time tau I. So remember, this is all Matsubara-Green's function, so this is all imaginary time, with this coupling constant that will involve the Coulomb interaction, right? So we derived this last class, and this interaction essentially resembles a diagram like this, where the interacting line, so to speak, is a phonon propagation mode. And as I mentioned, this has a finite propagation time. So unlike the pure Coulomb interaction, which we're treating as instantaneous, this has a finite frequency of Matsubara frequency. It has, of course, momentum, and the vertices also depend on the Coulomb interaction. So that's what we had in the previous class, where we get this effective electron-electron interaction coming from the phonons. So what we're going to do today is to combine that effective electron-electron interaction mediated by the phonons with the actual electron-electron interaction that we studied before, right? The one that comes from the pure Coulomb interaction V of Q, right? And here and throughout this lecture, we're going to consider the Gillian model, where the coupling constant for the electron-phonon interaction depends on the momentum only via the momentum of the electron-electron, the Coulomb interaction. This is actually not electron-electron, but electron core, electron ion interaction, but it's still the bare Coulomb interaction here, or rather its Fourier transform in Q space. We remember that this goes as 1 over Q squared, and this frequency is the plasma frequency that we derived in the class where we talked about the Gillian model and the phonons in the Gillian model. I'll also try to remember to put a link here. So my total Hamiltonian then has 3 terms. That free part that we talked about. Remember that now this is the Gillian model, so this frequency is not depending on Q, but we'll get back to that. But so far this is just a constant, is the plasma frequency. And there's the electron-electron interaction, and there's the effective electron-electron interaction mediated by phonons, which I'm already here putting in the interaction picture, since it involves this retarded part here. Okay, so but these two have a similar structure, right? Notice there is a VQ in here too, right? So this is going to be important. So what happens if I try to write an effective electron interaction that involves these two terms? So if I combine now, say that I write this one also in the interaction picture so that it becomes time dependent, and what I have is to sum these two Hamiltonians, I would get a very similar structure in terms of the operators, right? But then I'll have to add these two parts, right? Essentially the couplings, right? The one that depends here, which is the bare Coulomb, plus this, which is G of K, the vertex square divided by the volume. Remember there was a volume squared here, but one of the volumes there, and the free phonon propagator. Now, if I take the Fourier transform of this one and write this in terms of Matsubara frequencies, I now see that my effective electron-electron interaction will also be retarded, because this is a retarded interaction as well, and will have this form. In terms of diagrams, I could write this as a diagram that is wavy, like the bare Coulomb interaction, plus a diagram that, or an interaction line that is essentially the phonon propagator, plus the two points here in the vertices, right? The G of Q's. And we're going to do this calculation. We can actually get an expression for this, and we're going to see that this has a rather simple expression in terms of the bare Coulomb interaction and these Matsubara frequencies and the plasma frequency that comes from the coupling here. And we're going to see that even though this bare Coulomb interaction is always repulsive, right? Except that, well, if you put the minus sign here, in the case of the electron-ion interaction is attractive, but we're always considering the electron-electron term, right? So the electron-electron bare Coulomb interaction is always repulsive, but the effective electron-electron interaction can be attractive, especially for frequencies when you have frequencies less than the plasma frequency, okay? And we're going to see this derivation and how all this works in the blackboard. So let's go right there. So let's start by considering the fact of electron-electron interaction that we mentioned. So we have the bare Coulomb term, this wavy line, and we have the free phonon propagator, this curly line here with the two vertices. Remember, the vertex has a momentum associated with this. There's a Coulomb interaction in there, right? And we have the expression for the free propagated in the GLA model involves only the plasma frequency and of course the Matsubara frequencies. So let's do this sum, right? So we come here and replace this with the coupling for the GLA model. So we already see that we have these twos will cancel. There's omega squared there. So let's see. So there. So what we have, and then we do some algebra here. Essentially take this V of Q that appears both in the vertex and here, take it into evidence, get a 1 here, and then we do the algebra, get V of Q, IQ squared divided by IQN squared minus omega squared. So let's see this. There you go. So this was simple, right? Simple algebra. That's the result we had in the slide there. And what does that mean? I mean, let's try to see the meaning here. And where do we get that attractive interaction? Notice that the next step is to do the analytic continuation from these Matsubara frequencies, which are imaginary, into the real axis. And we discussed some of that in the class on Matsubara frequencies. Try to put a link here. Maybe it's one of the links that are already referenced, but essentially is the one that in the class where we talked about Matsubara frequencies. So once we do this analytic continuation, what do we get? So this is what we get. I mean, essentially you take IQN to omega plus, right? Omega plus a small imaginary part here. So this is the retarded potential, right? And then, yeah, you just take the analytic continuation. That's omega squared here. Now, notice that if omega is less than the plasma frequency, then this thing becomes attractive, or negative, sorry, and this effective potential becomes attractive. So if we would plot this effective potential as a sum of, as a function of frequency here, right, for a given momentum q, you would get something like that, right? That's essentially this form has this familiar shape, like the real part of a Green's functions. So you have, this is of course negative for omega less than the plasma frequency, and then it becomes repulsive for omega larger than the plasma frequency. So we see that the combined action of electron-electron and electron-phonon couplings can lead to an effective, attractive electron-electron interaction. That's one of the cornerstones of BCS theory, the fact that we can have that. So let's go back to the slide. Okay, so we derive the effect of Coulomb interaction, show that it can be attractive for real frequencies less than plasma frequency. And now let's go one step further and renormalize these interactions by RPA, like we did for the electron gas. So let's see how this works. Okay, so just to remind you about RPA renormalization, we did a whole class on that. There should be a link here as well. And essentially, we learned that if you try to do second order perturbation theory for the electron gas in the interaction, these plots explodes, and we found that the way around it is to renormalize the Coulomb interaction with these terms, these bubble diagrams, and we even calculated that. So is essentially V of Q divided by 1 minus pi 0 of Q times Matsubara frequency times the Coulomb repulsion, right? Same Coulomb repulsion here. And this, of course, introduces a shorter range for the effective interaction in the RPA language. And we want to do the same thing here. Essentially to avoid similar divergences that arise from the Coulomb interaction there, right? So what we're going to do is to write diagrams similar to those. So we have this effective electron-electron interaction that includes the phonons, and we're going to do an RPA version of that by essentially renormalizing it with the same bubble diagrams that we had here. So the equation that defines this effective interaction in the RPA approximation is similar to that, right? So just put the bare effective electron-electron interaction here, and I renormalize by this bubble diagram pi 0, which we already calculated. So another way to calculate this effective interaction in RPA approximation is to simply replace in the expression that we had in the previous slide. So the Coulomb potential, now we replace it by the RPA renormalized Coulomb potential. And we also replace both the coupling and the phonon line, the phonon interacting line, by their renormalized RPA versions. So this should be equivalent to this, okay? And we're going to see and calculate this and show that this effective RPA, this effective electron-electron interaction in the RPA approximation has a rather simple form. It essentially is the RPA interaction times IQN divided by IQN squared minus a renormalized plasma frequency that now depends on Q. And we're going to argue that it depends on Q linearly. So we're essentially talking about effective acoustic phonons here. So let's go to the blackboard and see how do we get this expression. All right, so let's take one step back and actually write, the RPA interaction in this form, which is equivalent to the form that we had. Is essentially this gives more the idea of the expansion, right, in terms of these bubble diagrams. So if I keep replacing the previous term here, I would have a notion of how this can be expanded in series. So the idea here is that to do the RPA, you just keep plugging these bubble diagrams in between interactions, so on and so forth, and do the expansion and resum it, right? So that's essentially the idea of the RPA. Now, as I mentioned before, if I do this sum of diagrams, this should be equivalent of essentially separating this expansion in terms that involve only the Coulomb interaction. That would be, the ones that will give me my RPA Coulomb interaction, right? So this would be this plus a bubble line connecting and so forth. And other terms that will involve the phonons that I'm going to group here in this GRPA and D0 RPA. So let's see how, this one we already know, right? But let's see how these two work. What is the expansion, the RPA expansion for, say, the free propagator? And here it shouldn't be, sorry, this shouldn't be D0. This is already the RPA. Okay, let me write there. The RPA right there. Well, because it's not the free phonon anymore, it's RPA. Okay, so let's see how this works. Okay, so this is the spirit of RPA, right? So this, by the way, I'm putting these minus signs here whenever I talk about these diagrams, just because the definition of them, right, is minus the time ordered of the operators and so on. So most of the times I'll be putting this minus sign. Sometimes they don't matter, right? So they cancel on both sides here. But just to try to remember that when I do these expressions in diagrams and I go back into the algebraic ones, I need to collect these minus signs. Okay. So what would be the expansion for RPA? And here again, I have this 0 that shouldn't be there. Okay, so let me erase this. So this should be at, let's write again. Why not, right? RPA here. And what is this? Okay, so this would be something like this sum, but now I'm using these curvy lines that are my free phonon propagators. Okay, so I have a free phonon propagator here, then a free phonon, a bubble diagrammed, another free phonon, and also remember this pi involves all the bubble diagrams connected by Coulomb interactions. That's how we did in the RPA. So it would be terms like one bubble, then two bubbles connected by one interaction lines, three bubbles connected by two interaction lines, and so on and so forth. So I'll definitely have these terms here that I have, say, two phonon lines, through free propagating phonon lines, and connecting, sandwiching a number of bubble diagrams connected by Coulomb interaction lines. Remember, this is free interaction. So this is minus V of Q. And this is the pair of free propagating fermionic lines. Okay, so this is the expansion for the RPA. And of course, here, if I have, say, three propagating lines, three phonon propagating lines, each of these two bubbles, I can express this in terms of more bubbles coupled by interacting lines and so on and so forth. So you can think of this as each of these terms will generate many infinite other terms with interacting lines and so on, so forth. Okay, and I have to add all of them to get my RPA renormalized phonon line. One way to see this sequencing that I'm doing with this dotted line in magenta here is that I treat this as a bubble RPA. Okay, so two phonon lines sandwiching a bubble of RPA. That involves all the diagrams with, say, bubbles coupled by interacting lines here. Now these two will give me three phonon lines, three free propagating lines with two RPA bubbles. And I keep going, and right, so now I have, next is four phonon lines with three RPA bubbles and so on and so forth. So but that's essentially the expression that when I add all of this will give me my RPA, this curvy line here with a double line. All right. So now if I take this series and essentially write this as a Dyson's equations, right? So I just take, this part here, and notice that this is the same repetition of diagrams here. This is exactly minus the RPA, and this is the renormalized bubble diagram. And then the Dyson's equations will become something like that. The RPA equals the free propagating line, and here I'm using this notation of key tilde, which includes both the momentum and the Matsuburg frequency, and that will be 1 minus pi RPA times this times the vertex, right, and d0. So this is the expression for the RPA in terms of the free propagating line. In other words, this is just solving this Dyson's equation. Okay, so that the formal solution, of course, I would have to calculate everything. So let's take a look at the vertex now. So why would the vertex be renormalized by RPA as well? So let's take a look at the vertex, and here I'm adding just the these tiny lines just to make sure that we understand the expansion that we're about to make. So the typical phonon vertex, the one that is not renormalizing, looks like this one. Okay, so we have here, this is just GQ, okay? So here's GQ as well. And what is the difference between that? What do I renormalize? So I essentially insert a bubble diagram and an interacting line, VQ, here, that's VQ, and that's pi 0, right? The term between whatever the free propagating line of the phonons and the propagating lines for the electrons. So I have this term here, and then essentially I'm inserting the full RPA vertex here, right? Pretty much something similar to that, which then the next term would be another bubble diagram with another interacting line. So I keep renormalizing the interaction, right? So, and then I'll get the series of bubbles here. Notice that this essentially comes from the fact that I have a view of Q inside the vertex here, and this has to be renormalized by these bubble diagrams, right? So once I do that, I also get an expression, which is essentially this one. So notice that what's in here, right, is precisely that sum of diagrams of bubble RPA that I had there. So I had 1, then I had 2 connected by interacting line, now I have 3. So this series, which I'm calling here, let's put this in magenta. So that's this, now this, now this. All of these will go into this bubble diagram, just like we had there. So that's essentially the renormalization of the vertex here, GRPA, and this is G1. This is, say, if you want G1 interaction times the RPA bubble there. And then what I get is this. I get that GRPA is GQ plus GQ times V times pi. It's essentially this diagram is GQ plus GQ here times an interaction line times pi RPA, which I'm defining the inverse of this as this epsilon RPA of QIQ, and this is nothing more than the electric function in the RPA approximation. And just a quick note, so let's just scroll down here a bit. Just to remind you that this is 1 over epsilon RPA, and you can actually show that this is equal to 1 over 1 minus VQ of pi 0 Q. Why is that? Well, if you remember, essentially you can write this sum of RPA diagrams as, again, a Dyson's equations, and you can solve it, and that would be pi 0 over 1 minus VQ pi 0. So if you multiply this and add 1 by VQ, you would have essentially, right, so if you multiply this by V of Q and multiply by, and add 1, so 1 minus this on top, you would get precisely this result, right? So, and this is 1 over epsilon RPA, and just to remind it, and this is another point that I should point out that we're going to need later. This epsilon RPA is essentially what defines the RPA potential. Just RPA Q IQN equals the bare Coulomb potential divided by epsilon RPA Q IQN, which is precisely this. All right. So in other words, the renormalized vertex here, again, I'm just dividing by epsilon RPA, just like the RPA potential is just the bare Coulomb potential divided by this dielectric constant in the RPA approximation, okay, which is, again, 1 over this. All right, so let's keep going, and now let's put everything together to calculate the effective potential. Okay, so now to calculate the effective potential, we already calculated the renormalized vertex. So it's GQ divided by epsilon RPA. We calculated the renormalized phonon line, D0, 1 minus pi RPA, 1 over VR GQ squared, D0 of Q. And this Q is already, including both the momentum and the matter frequency. And for the Gilliam model, we have, these expressions. So let's now calculate this explicitly. Okay, so let's do it. Let's start with this one, which is D0 of Q, which is this, 2 omega IQ squared minus omega squared, divided by this. So I put all this in minus 1. This is pi RPA, which we already know from the previous slide or the previous calculations, that this is 1 over ERPA minus 1 divided by V of Q. Okay, so that's what we had in the previous slide. Yeah, and so just to remind you where this comes from, remember we had the previous slide, we had 1 plus VQ pi RPA equals 1 over epsilon RPA. So then I have, of course, pi RPA equals 1 over epsilon RPA minus 1. Oops, this one is minus 1 over VQ. Just so, well, this might have, I'm not sure if this fell over the screen there, but this is 1 over IVQ, which is precisely this. So this is pi RPA. Okay. Now the vertex, which we have 1 over V in the Gilliam model, this is 1 over V times the vertex, the coupling, the bare coupling squared is 1/2 VQ omega, and I have the propagator here, 2 omega IQ n square minus omega square, all this to the power minus 1. So now this of course cancels here, there's this 2 here that cancels as well, and then I go and there will be this 1 minus 1 over RPA, right? And now I'll multiply this 1 over RPA minus 1 times this omega square that I have here. So I have omega square over RPA with a minus sign plus omega square, which is this one. And then all this has this 1 here. So I'm going to write this one as 1 over IQN squared minus omega squared over IQN squared minus omega squared, common denominator. Then I have IQN squared minus big omega squared. There's a plus omega squared coming here, which will cancel. And there's this minus omega squared divided by RPA, everything to the power minus 1, right? So you see that there's going to appear this omega squared divided by the electric constant in the RPA approximation. So these minus omega squared cancels with this one. This is to the power minus 1, so this denominator will cancel with this, and this will go into the denominator. So final answer is 2 big omega IQN squared minus omega squared divided by epsilon RPA, and this now will depend on Q, right? Notice that epsilon RPA, of course, depends on the momentum and the Matsubara frequency. So the final result is going to be this. The RPA is going to be 2 omega divided by IQN squared minus what I'm calling omega tilde squared, which now depends on Q, on both the momentum and Matsubara frequency. So this is the RPA renormalized plasma frequency, which in the Gillian model was a constant. Now when I renormalize it by the RPA dielectric constant, or sometimes called the polarizability, depends on the contest, this is a renormalized frequency, and now this will depend on Q. And I will argue here, and I'm not going to show it explicitly, that for small values of Q, this would go linear with Q, okay? Essentially because epsilon RPA will go with 1 over Q squared, and then, well, this omega, the renormalized omega is omega divided by the square root, so is going to be linear with Q, okay? So that's the main point, and this is going to be then kind of an acoustic phonon once I renormalize by RPA. Now let's see what happens to this guy. So let's scroll down a bit. Yeah, before that, let me just write this down, what I just said. That omega Q is linear with Q, since this is what? This is 1 over square root of epsilon RPA. And epsilon RPA is 1 over Q squared for small values of Q. And so this goes as a acoustic phonon, okay? Now, so let's go now to GRPA. Well, so better yet, we're going to calculate the whole thing, right? That second term in V effective. So 1 over VR, the GRPA squared dRPA, which we just calculated. So this we know is GQ divided by epsilon RPA, so everything is squared. There's going to be a 2 omega IQ, and this is this omega, remember, is not renormalized yet. It's going to be 1 over IQN squared minus now the renormalized omega, and this should be a Q, not a P. So let me correct that. This should be a Q. That's a renormalized plasma frequency, which is acoustic, as we saw. And notice there's now going to be one of these epsilon RPAs will renormalize this, and the other is going to renormalize my Coulomb potential that comes from here, right? 1 over VR GQ equals 1/2 VQ epsilon RPA. So this 1/2 cancels with these two, and I get this VQ divided by epsilon RPA, okay? The other epsilon RPA goes to renormalize the frequency, so I got this expression. And now notice that this, of course, is the RPA potential, as we saw in a previous slide as well. So what's the result? Yeah, just to make sure that this is VRPA. So let's see the result. So putting everything together, we have VRPA plus this times plus this, essentially. I have now VRPA omega q squared divided by IQN squared minus omega q squared. So putting VRPA in evidence here, there's going to be 1 IQ squared minus omega q squared plus this omega q squared. These two will cancel, and I get this. VRPA effective equals VRPA times IQN squared minus omega to the squared q, which is the final result that we had in the slide. So this is a rather simple expression. Notice that it's still attractive, right? Even though this one is always repulsive, this one can be attractive for frequencies smaller than now my renormalized plasma frequency. Okay, the point is that now this will depend on Q. So, but still, for frequencies smaller than this one, it will be in a, how to say, an attractive potential between the electrons. All right, so let's go back to the slide. So we just derived this, and this we introduce here the renormalized plasma frequency, and you argue that this is linear with Q for small values of Q, so this behaves like an acoustic phonon. So, okay, so now I have an effective attractive potential for frequencies smaller than this renormalized frequency. What does that mean? So let's go into see the instability caused by the fact that this can be attractive, so that the electrons not only will attract each other, but they might also form bound states. Okay, so to conclude this class, we're going to consider the discussion on the pair scattering and the possible formation of bound states between electrons due to this attractive electron-electron interaction. So let's consider the following pair interaction, meaning a scattering event mediated by Coulomb repulsions, and we're actually calculating this vertex, meaning that we're calculating the series of scattering events with an increasing number of interacting lines, right? And these scattering events actually, they are a special class where I'm gonna consider time reversed states of electrons. So meaning that you have an electron going in one direction and another electron coming in the opposite direction, so that these two electrostates are exact time reversal of each other. And if they're time reversal, of course I have to reverse the spin too, right? So the time reversal operator reverses spin. So essentially I have an electron with spin up going in one direction and another electron with spin down going in the opposite direction. I'm drawing here with the lines going in the same direction, but I'm reversing the momentum case here. But just to give an idea, this is just scattering events of electrons with opposite momenta, so that if there is an attraction between them and there's eventually the formation of a bound state, this bound state will have zero net momentum, right? And zero spin as well. It'll be a singlet. So let's just illustrate this diagram here. Just this first diagram, just to notice what I'm talking about here. Okay, so let's go to the blackboard real quick. Okay, so just to give you an idea of what I'm talking about these time reversed states, let's consider this situation, right? So we have this time reverse state. So I have an electron here going with momentum k positive, and this is positive upwards with spin sigma. And it's going to interact with an electron coming here with momentum minus k and spins down, okay? So then they are scattering, right? So they will interact via that effectively attractive electron-electron interaction mediated by phonons that we already calculated, right, with the RPA. So this is minus VRPA effective, which will carry momentum, right? So where's the momentum here? So let's see what goes in there. So spin is conserved and it's carried only by the electrons. So this interaction doesn't carry spin. So whatever the final momentum here will have a state with spin down. We're going to figure out what is this one. Let's look at let's say that our momentum here, a final momentum is P, okay, spin up. So let's conserve momentum in this vertex. So here, let's point my little arrow this way so that, you know, K is coming in, P, and this momentum is going out. So in order to conserve momentum, the sum of this with this has to be equal to K. So this should be K minus P, right? And this includes of course, the Matsubara frequencies as well. Okay, but let's just, yeah, you can put a tilde here if you want. Now, if I'm going in with minus K here, and I'm going with plus K, of course, this minus this momentum has to be minus P, okay? So everything here is as it should with the momenta already taken into account. All right, so let's go back to the slide. So now this vertex involves multiple interactions like this. So if I keep conserving momentum, I'll always get this K minus whatever's in here. So K minus K1, or if you want this plus this, right? That's the momentum. So K plus K1, now K1 plus P minus P, sorry, K minus K1, K1 minus P, K1, K2 minus P again, and so on and so forth. And that's the type of diagram that, or pair, that we can evaluate using, say, a Dyson's equation. So let's see how it works. So if I remove the outer legs and I only look at the square, so this sequence, this plus this square here plus this other one here, what I get is something like that. The VRPA effective, remember there's this minus sign wherever I put it, write the diagram, V of RPA K minus P plus this K minus whatever K is coming, is the one that's coming here, right? The line, the free Fermi line here. K minus Q times the remaining of the same vertex, since this structure keeps repeating itself. So if I look here, for instance, is K minus whatever's in here, I'm calling it Q, and whatever is in here is precisely the same lambda with a different momentum coming in, but it's the same lambda. So what is this diagram? So whatever I'm calling here lambda of, say, K minus P is V minus effective, and here's going to be lambda of Q minus P, right? P is whatever's coming in this line there, minus P there, okay? So there's these two other free propagating lines, three fermionic propagating lines that propagate from this point where with a momentum q, and this one propagates with a momentum minus q, or propagating this way with a momentum q if you want, but they have opposite spins. And so this is a Dyson's equations for lambda that we could in principle solve, since we know the expressions for this, which we derived in the, just now, and we know the expressions for these propagators, so we could in principle solve that. And this has been done, of course, but here we're going to do a simplification that will allow us to solve for lambda in an algebraic way. And this simplification, even though it's kind of drastic, but still keeps the main information that we need in order to describe the physical properties of this kind of scattering and this formation of pairs. So let's see how it works. So the approximation is that we're going to trade all that expression that we derive for the effective RPA potential and replace it with this simple form. Is attractive for Matsuburg frequency is less than the bifrequency and zero otherwise. And we're going to do some justification of why that is. But once we do that, we get a very nice algebraic form for lambda. We're going to derive that. And this will lead us to a denominator that can become zero if this Matsubara sums that appears in the denominator equals to 1. So that I have 1 minus 1 equals to 0. And that's precisely what we call the Cooper instability. All right, so let's go to the blackboard and try to make sense of why did I choose this rather drastic approximation for my potential and how we get this algebraic form for lambda for the pair scattering vertex. So let's see how this works. So the first thing I'd like to point out is once we have that expression for V effective RPA, we get something like this, right? We already argued that these omega, this is actually, let me just put here that this is the renormalized plasma frequency that I argue that goes linear with Q for small values of Q. And if you remember in the class on phonons, we discussed about the Debye model that would essentially take an acoustic phonon up to some momentum Q Debye, where at this momentum this frequency equals to the Debye frequency, and that's kind of the cutoff frequency and momentum for a model. And this would be essentially defined so that the density of ions would be equal to the density of electrons, right? Or the number to ensure charge conservation or charge neutrality in the system. Okay, so if I now put this into my effective RPA interaction, and there should be like an RPA here, and we saw that, right? That this for real frequencies smaller than whatever this frequency is, and let me put this is a tilde, this the renormalized frequency, this would be attractive and repulsive otherwise. Now, what I'm going to do is I'm going to take this to be the Debye frequency, and that's the key approximation. And why is that? Well, essentially, since the phonon density is much smaller in this region, remember it goes with the energy square, the interaction itself will only be effective on frequencies around this region, which is precisely the largest momentum for the phonons that I can get. So, the contribution from this region will outweigh the contribution from this region by quite a bit. So, in that sense, even if I have omega even though omega cube might be here, the contribution from frequencies around omega d will be much larger than this. So that justifies replacing omega tilde q by its value at the Debye frequency. So what I'm arguing is that replacing this with this, right, a step function right at the Debye frequency, is reasonable. I mean, it's a quite a drastic simplification, but it keeps the main ingredients of my model. And so what happens for the repulsion? Well, for the repulsion part, the repulsive part of what I'm taking to 0, we know what's happening here. This will lead to screening, right? So there's a short range potential in the RPI, so there would be like in a Thomas Fermi approximation or something like that. These will be screened and essentially renormalized, become just a Fermi liquid, if you want, a Fermi liquid contribution, which will be what's going on here is just going to be same old metal as it always was. I'm really interested in this transition here and what happens when this becomes attractive. So this rather simple model captures that nicely. Okay, so let's keep going. So if I now replace this by a constant for frequencies less than the Debye frequency, it means that my sum over frequencies here will go up to only the Debye frequency, okay? So that's a cutoff, at higher frequency, so the omega Debye. Still have the sum over momentum, but the interesting thing is that nothing here will depend on momentum. It's just a constant, right? So I just take this and replace by minus v, so I got a plus here. And this is a plus v here, right? So that's lambda. Lambda, of course, will not depend on the momentum anymore, since this doesn't depend on k, right? So this does not depend on p. So if this doesn't depend on k and p, this will not as well, right? So this will be just a constant. And what do I need to calculate this is just to evaluate this integral and this sum. And for that, we need the following. We're going to define this integral in Q and the sum in Matsubara frequencies as like a Matsubara sum S of beta. So this will definitely depend on the temperature, since it will just be a Matsubara sum. So, and this doesn't depend on the potential, and on lambda is just an algebraic factor. So my expression for lambda becomes v plus v lambda times SB, and I can then solve for this algebraically, and I get lambda equals v divided by 1 minus v SB. And as we mentioned before, this diverges if VSB equals to 1, right? So I get a divergence here. And this is the divergence that we'll be focused on. That's our Cooper instability. And this will happen at a certain temperature. It will depend on the temperature, since this thing depends on temperatures. So let's try to calculate V of SB and see if we can calculate at which temperature this will diverge. So let's scroll down a little bit. Okay, so I rewrote my sum, or V times SB. There's the V here. 1 over the volume of sum over Q, the momentum, and then a Matsubara sum. 1 over beta IQN. So in absolute value, so I can have positive or a negative. So it goes from minus omega d to plus omega d, right? So the absolute value will go from, say, 0 to omega d. And these are, again, fermionic frequencies. So they change depend on the temperature like this. Qn is equals pi over beta times an odd number, 2n plus 1. Now, of course, I want to take the continual limit here. So 1 over v sum over q goes into integral. This is, this should be a 3. So the 3-dimensional integral goes to the volume in q space, right? Oops. Sorry about that. And I can actually replace this, and we did that in the class on the electron gas, by an integral in energy using the density of states as my weight, right? So this would be an integral from 0 to infinity of, right, so I'm considering all temperatures here. So rho of epsilon, and whatever is the integrand here will also be there. So let's write something like this, and there will be like an integrand here too. All right? Okay. So now let's use this to try to evaluate this sum. So I have now replaced this with the integral in energy, and now I'm replacing since this density of states is symmetric in energy, I can do this trick of taking the integral from minus infinity to infinity and put a 1/2 here, right? So that's what I'm doing here. This factor of 2 goes here, and now I have the Matsubara frequency and this integral of what? This is the complex conjugate of this, right? Remember, we have Green's functions with opposite momentum, opposite Matsubara frequencies. So this would be epsilon q square plus qn square, right? And epsilon q goes to epsilon, the energy, when I'm replacing this integral in momentum with an integral in energy. So I just need to evaluate this. So one trick that I'm gonna use essentially, and this is actually an approximation, that for metals everything will happen around the Fermi energy, where this density is pretty much constant. Remember, this goes slowly with energy, and over a temperature range, or not a temperature range, but over a range in energies around the Fermi energy, this is essentially constant. So I can take this out of the integral and take its value at the Fermi energy, since this doesn't have much structure around the Fermi energy. That's where all the action is going, right? So, typically in metals, if it was a different system, then you might worry about, you know, things like resonances and you know, divergences or something like that. But for a 3D metal, this is really very smooth. So I take this v rho of f, and I'll give thus the order of magnitude. That's what we're looking at. V times the density of states at the Fermi energy times, now I can integrate this, right? And I try to evaluate the sum. So this integral, if you do it, will give you pi over the absolute value of this. And the sum in Matsubara frequencies, notice it goes from omega d to plus omega d, or to minus nd up to plus nd, where nd is n such that this is equal to the Matsubara frequency. So you can calculate nd equals beta omega d, right? When this is omega d divided by pi minus 1 divided by 2. So that's nd. So that's my sum. I have to calculate the sum, this sum here. Okay, so at the end of the day, I have to calculate this sum, all right? And notice that a lot of things simplify here, there, this beta cancels, these pi's here cancels, and now I change my n to an n prime so that this n prime starts at 0 and ends at 2nd. So instead of going from minus nd to plus nd, I'm going from 0 to 2nd. And now I have this sum going from 0 to 2nd of 1 over 2n prime plus 1. So to evaluate the sum, I can call this, let's call this m. So m equals, let's see, m equals 2n prime plus 1. So when prime is 0, m equals 1. And when n prime is 2nd, m is 4nd plus 1. And this sum over 1 over m for larger values of, k here, the maximum value here, I can approximate as, say, the integral of 1 over x, right? That's the definition. And this would be essentially the log of k minus log of 1, so that's be log of whatever is in here. So this would approximate to the log of 2nd. And 2nd is what? 2nd is 2 times this would be, this would be 4nd, right? So this would be 4k equals 4nd plus 2. That's when n prime equals 2nd, 4nd plus 1, sorry. So then would be 4 times this would be essentially the log. So that's the final result for VSB as beta. And notice that this can be equal to 1. How? If this equals to 2 over V rho F, or this would be the exponential of 2 over V rho F, VSB equals to 1. So if I solve for beta, right, this will happen at a critical temperature, which is essentially the bifrequency times an exponential factor. But for temperatures below or at or below this frequency, or, well, let's see, for temperatures such that this will hold at the pair vertex amplitude will diverge, okay? So in this case, there will be something happening. So that formation of those pairs of electrons with time reversed states. So spin up going in one way, spin down going another way, they will interact, and they will strongly interact to the point that they might form a bound state at this kind of temperatures. Notice that this can be much smaller than the Debye frequency or the Debye temperature. So we saw in a previous class that the Debye temperatures can reach, say, 100 Kelvin or so. But there's this exponential factor that will depend on V, and it will depend on the density of states at the Fermi energy, right? So, of course, these appear in the denominator here. So the larger either the potential or the larger the density, the larger will be this critical temperature. But still, if this is in exponent, in the denominator of the exponent, so even for sizable amounts, for metals, for instance, this could be a factor of 10, 1 over 10, right? To reduce from the Debye frequency. So that's why, even though you have Debye frequencies that can be large, or Debye temperatures, say 100 Kelvin, this can be like a 1 Kelvin or 2, okay? Because of precisely this exponential factor. But nonetheless, what I'm saying here, the result, even for this very simplified model, tells me that there might be a transition where this pair of vertex will diverge. And that's what we call the Cooper instability. Okay? All right. So we saw that this factor here will acquire this form, and there's definitely a frequency where this can diverge, or a temperature. And this is the critical temperature for that is related to the Debye frequency. And as I mentioned, even though this might be large, this the larger the Debye frequency, the better. The larger the temperature, the larger the density of states and the potential, the better, because this will increase the denominator, the exponent will decrease, and this overall critical temperature can increase. But for metals, this still a sizable reduction, can be a factor of 10 or so. So you were talking about temperatures which are 10 times smaller than the typical Debye temperature. Could be, if we're talking about 100 kelvins, this could be 10 or so, or maybe, in that region. So for metals, you don't expect this to be and when this theory holds, this to be much greater than or to the of, you don't expect this to be the order of the Debye temperature, but still something will happen at this temperature, and that's the onset of the superconducting state due to this Cooper stability. So in the next class, we'll discuss more about that and see how can we have a theory that describes this state in a microscopic way. All right, so that's it for this class, and we'll talk next class.